Hey, thanks for joining me. So we're going to look at electron configurations, and it turns out this pretty much explains everything else in the course. So all of chemistry is ultimately dominated, I would say, by the configuration, the arrangement of the electrons around the atom. So it's really important to know this stuff. Now, how many electrons does an atom have? Well, we said earlier that atoms are completely neutral. And that means they have no charge whatsoever. So if you're hydrogen, and hydrogen's got the atomic number 1, remember we write the atomic number to the bottom and to the left of the element symbol. That's a Z, not a 2, by the way. And that tells you it's got 1 proton. And how do you know that? On a periodic table, that's the number written above there. So it's got 1 proton. If you've got something like, say, carbon, carbon's atomic number is 6. How do you know? On a periodic table, you see a 6 written above the symbol. Notice on the nuclide symbol, we write the atomic number below and the mass number up above. The mass number is not going to affect the protons or electrons, so I'm just going to neglect to write these. But the 6 protons there is given by the atomic number. So if it's got 6 protons, then the question is how many electrons does it have? And the key is if atoms are neutral, they must have exactly the same number of electrons. So hydrogen must have 1 and carbon must have 6. Now we'll meet later on these things called ions, and ions actually have a charge, so they're atoms that have gained or lost electrons, but it's important to remember at this point that atoms have no charge, so the number of protons and electrons have to match for those charges to cancel out. Now we're going to look at a simpler model of electron configurations that we'll be able to use all through this course. There are more complicated models that are better, but it turns out to understand the things we need to understand in this course, we won't need to look at orbitals and S and P and D and F and whatnot. So this is a little simplified, but actually it contains more than enough detail to get by. So what do we say? We've got a nucleus of an atom. The nucleus of an atom is where the positive charge is, so it's where the protons are, and the neutrons don't have charge, but the protons do. And surrounding it, we find that there are shells. There are sort of like orbits where the electrons can live in. So I will go ahead and kind of write it like so. And I've written a little box because I'm going to put a number in there. This is the first shell, so I'm just going to write first shell here. There is a second shell that's much bigger. And in fact, I'm not going to be able to draw the other side. And it turns out, well, I'll just go ahead and tell you, right? So it turns out that 2 electrons maximum can fit in the first shell. And in the second shell, you can have 8 electrons maximum fit in here. So the first shell, the second shell, something like that. And you might guess as the atom gets bigger and bigger, more electrons can fit in the shells as we get further and further away. So there's more space further out. So if you live in the suburbs, there's more space than if you live in the city center. And that is true. But we're going to tell a little white lie here. We're going to say for the first 20 elements, and the first 20 elements are biologically probably the key elements to understanding how our body works. We're going to say that the third shell can only hold 8 electrons in, and the fourth shell at this point is only going to hold 2 electrons in. So we're going to restrict ourselves to these configurations, these number of electrons in the shells, although as we go down the periodic table, this isn't actually obeyed. So the first 2 are definitely correct. Don't ask me to explain why that's not really 8. It's actually 18, and that's actually not really 2. It's 36. But this will do for now. If we just restrict ourselves to the first 20, this is golden. So let me show you the periodic table and show you which elements this is obeyed for. So here's the periodic table from the textbook. So we're really just going to be using this for elements 1 through 20. And so these are the main ones. In fact, biologically speaking, the main ones. So I was taught way back when in high school biology that the most important elements for biological life. And I know every element has some kind of role to play. So iron clearly is part of the blood system, right? That carries oxygen around. And zinc is part of a finger that actually keeps proteins in a particular shape. So nothing is completely irrelevant. But nitrogen, carbon, hydrogen, oxygen, phosphorus, sulfur. These are the big elements here. And of course, in bones, you've got calcium as well. And they are present right here. So there's nitrogen, there's carbon, there's hydrogen, there's oxygen, phosphorus, sulfur, calcium in bones. So they're all in the first 20. So you can think of almost every biological molecule as containing one of these atoms. And if we want to know how they're bonded, how they're joined together, their three-dimensional shape, their polarity, all that nonsense, then you're only going to need to know it for these first 20 elements. And the electron configurations of these first 20 elements should be totally fine. So let me show you how this all works then. So I should go back to those shells, right? So the first shell can hold a maximum of 2 The second shell can hold a maximum of 8, the third shell 8, and then the fourth shell a maximum of 2 electrons. And since the nucleus is all the way on the left, we might expect, since the electrons are negative and the nucleus is positive, that they would prefer to hang out next to their friend, the nucleus. And that is indeed the case. So when you put the electrons in these shells, they will tend to hang out in the shells close to the nucleus. So let's go ahead and draw that in. So here's my nucleus right here, and here's my first shell. And these are the ones, right? So you're going to a show or something, right? You want to sit close so you can see the people playing. And obviously the nosebleed seats, right, are very far away. So if you're far away, right, it's not as exciting. So the electrons prefer to be close to the nucleus wherever they can. But, you know, there's only so much room in each shell. So they have to go to a second or a third or a fourth shell in order to fill up. So how does this work? Well, if we have something like hydrogen, which is element number 1, we just got 1 electron. And by the way, I'm going to write now what I'm going to call the electron configuration, or E- config for short. So that's the arrangement of them. If I go to something like helium, helium's got 2 electrons. They can both fit in that shell right there. But the interesting thing is when you get to something like lithium, lithium's got 3 electrons. So 2 of them can go in the first shell, but the third one can't go in the first shell because it only holds 2. So that third electron goes into the second shell, and so on. So if you go to element number 4, which is beryllium, then 2 of the 4 electrons go in the first shell, and the remaining 2 go in the second shell. And remember, the number of protons is the number of electrons. So this is just telling me that I got to keep track of my electrons. So what comes next after beryllium? I think it's boron. So 2, 3. And then it's our friend carbon, 2, 4. And what do we have? Element number 7 is nitrogen, so 2-5. And after that, the 8th element is oxygen, so 2-6. And then the 9th one is fluorine, so 2-7. And then the 10th one is neon, 2-8. So to look at neon, right, we got 10 protons, we got 10 electrons. 2 of them could go in that first shell close to the nucleus. We run out of room. And then the 8 remaining ones can go in the second shell. Now, if we go to element number 11, which element 11 is sodium, and if you look at it on your periodic table, it's in group 1A. So what group is that? That's right, it's the alkaline metals, not the alkaline earth metals. And so if you've got 11 electrons, 2 can go in the first shell. That leaves behind 9. Of those 9, 8 can fit in the second shell. That leaves you 1 remaining. It's got to go in the third shell. And if we go on down to element 12, so element 12 is magnesium, then essentially it's 2, 8, so that's 10 electrons accounted for. You got 2 more left. They can go in the outer shell, something like that. So you should probably go ahead and make sure you can write all the ones from magnesium all the way down to calcium. And calcium is actually 2, 8, 8, 2. So at that point there, everything's completely full. Now, here's the really cool thing. Here's why I think electron configurations explain everything. And this is why I am a massive fan of these. If you take something like lithium, which is an alkali metal, and you take something like sodium, that is an alkali metal, what you notice is that they all have 1 electron on their outside shell. And this means that the atom of lithium only exposes a single electron on the outside of the atom, and an atom of sodium only exposes a single electron on the outside. In fact, that outer shell is the most important shell in chemistry, and the outer shell we call the valence shell. So not valence, valence. And the inner shells we call the core. So the 2 and the 8 here and the 2 here, these would be the core, and I should switch to blue, and this would be the valence. So notice that the group 1s have 1 valence electron on the outside. Now if you went to group 2, the alkaline earth metals, so you've got something like beryllium, and you've got something like magnesium, and you've got something like calcium, then you should notice that they all have something in common, right? They all have 2 valence electrons on their outer shell. So the very outside of the atom's got 2 electrons in it. So, and that's actually the secret to chemistry. So the behavior of the atoms is almost always due to the number of electrons on the outside, the number of valence electrons. So that's really it. All those core electrons, all those protons and neutrons, they are really not to worry about too much. It's the number of valence electrons we have to worry about. So that is the big secret. And if you notice, there's actually something else. Let me go to a new slide and show you. If you look at an atom in say group 3A, or I could write it 3A, I'm sorry, like that. That would be something like boron or aluminum. In fact, why don't you go ahead and pause this video? Boron is element 5. Aluminum, I believe, is element 13. And write their electron configurations out and tell me how many valence electrons each one of these has. So pause the video and... okay. I'm right back. I guess I shouldn't have paused mid-sentence, right? So the electron configurations are 2-3 for boron. For aluminum, you got 13 electrons, so 2 go in the first shell. That leaves you 11 left. All those 11, 8 can go in the second shell. That leaves you with 3 left, and 3 go in the outside shell. So if you notice, all of these have got 3 valence electrons, and you might start to see a pattern here. And the pattern is almost always the group number is the same as the number of valence electrons. So almost always, with I think one common exception, the group number is the number of valence electrons. So make sure you highlight that and underline that doubly in your notes. There's only one time where that's not true. And if you look at helium, and actually, let me go ahead and do neon and argon for you. So actually, maybe stop the video and write down those electron configurations. See what you get. Pause the video, have a go. Okay, I'm back. So if you pause the video and had a go, you should have 2 for helium, you should have 2-8 for neon, and you should have 2, 8, 8 for argon. And actually, if you notice these, right, oh gosh, it doesn't work, does it? So although these are group 8A, and I said earlier the group number is the number of valence electrons, that's actually true for everything. But helium, right, that's actually an exception. So we have to remember that, right? So some periodic tables actually put helium in a different group to match the electron rule, but it doesn't really react the same as the other elements in group 2A. So we typically leave it in the noble gases. But if you notice, they do have something in common. And the thing they have in common is that that outer shell is completely full. You can't put any more electrons in there. And so that's actually what makes the noble gases so inert, right? They're inert because they've got full outer shells. And in the next chapter, we will see that that desire to fill up that outer shell, which is almost the desire to eat food, to have a full tummy, right, makes the atoms join together and share electrons or donate electrons to form molecules and ions. So all they're always looking for in life is just a full outer shell. So very good. I think that is everything we need to say. That is the end of the chapter. You've done great. This, I believe, is the end of week 3 of the class. So awesome sauce. So don't forget, there's a quiz on this material on Blackboard. And I guess I'll see you next Monday if you watch them on Monday. Bye-bye.